always, sometimes never. This time we want to decide whether it is always, sometimes, or never true that the dot product of x with y is the same as the dot product of y with x. In other words, we want to decide whether dot product is commutative. Well, I'm going to share with you a processing secret of mine. What I end up doing is trying to figure out what this notation actually means, and I use some scratch paper and I write out what the dot product of x with y actually is. It's actually the sum from 0 to n minus 1 of the components in x times their corresponding components in y. The dot product of y with x is the sum from I equals 0 to n minus 1 of psi I times chi I, the component in y, times the corresponding component in x. Then I looked at these two. I'm trying to decide whether these would give me exactly the same solution. Well, I noticed the difference between these two sums is just the values that we're trying to add up. But here I'm adding the chi I, psi I, and here psi I times chi I. And I know that these are just real numbers, and real number multiplication is commutative, so these actually will give me the same results, which means because real number multiplication is commutative, dot product is also commutative. All of the proofs that I've been doing in this section have been trying to determine whether we can extend some of the properties that hold for real numbers to vectors. Well, we've just now determined that dot product is most likely commutative, but we need to formally prove it. So let's do that. We'll start as usual with assuming that x and y are just arbitrary vectors of the same size. They need to be the same size, otherwise we cannot perform the dot product. So we'll let x and y be arbitrary. And I'm going to start with the left-hand side. If you want, you could start with the right-hand side. Doesn't matter. And show it's equal to the right-hand side, in my case. X transpose y, we already mentioned by definition of dot product, is found by adding components from 0 to n minus 1 of the components in x, I'll call them chi i's, times the corresponding components in y, I call them psi i's. But I mentioned these are just real numbers, and real number multiplication is commutative. So this is the sum from 0 to n minus 1 of psi I times chi I. We can switch the order in which we multiply each component. And that's just because real number multiplication is commutative. Notice I like to write shorthand notation. Again, I hope you can read it so that you can understand my thinking. But this is just by definition of dot product what I had written in my scratch paper earlier as the dot product of y with x. And so we're done. It is always the case that x transpose y is equal to y transpose x. And remember, this is the notation that we use for dot product. And so what we have shown is something very important. Dot product is commutative.